This is okay. All right. So today, this video is about the topic work energy equation. All right. So previously we have used the equation F equals ma, which is the Newton's second law, and during section 4a. Right? And this is the equation we've been using at step 5 to solve the unknowns such as forces or accelerations. And today we're gonna look at this equation in more detail. So let's look at the right hand of the equation. Let's look at this acceleration A. What if, let's put ourselves in path coordinate system. If we're in path coordinate system, if you can recall, acceleration A equals v dot et hat plus v squared over rho en hat. This is the formula for acceleration in path coordinate system, right? If we can substitute this A into F equals ma, we will get something like this. Forces equals to m, that's a mass, times v dot et hat plus v squared over rho en hat. Okay. Now, if this acceleration has two directions. One is on et direction. Another one component is on en hat direction. And as we learned, et hat represents the direction of a tangential direction, which is the motion of the object or the particles. En pointing to the center of curvature, right? So in this term here, or this term here, it has a name. It's called rate of change of speed. Remember that? This was in one of your quiz. Okay, and this term here, the term of the et hat here, it changes the direction. Only has something to do with direction. So this term has something to do with change of speed, and this term has something to do with change of direction. Okay, so which means, and only et, it's what related to the change of speed. And in the work and energy equation, we only care about the forces that can change the speed. So we care about the force in et hat that change speed. Alright, okay, so if we only care about the forces in et hat direction that change the speed, how can we extract that force on et direction from this formula? There's one thing we can do is by using dot product. That what we learned in chapter 1, chapter 2. It's also on your book, page 11. If we take dot product on the direction we care about, we take the dot product of the unit vector, which is et hat. That is, oops, let's change color here. That is m v dot et hat plus v squared over rho en hat dot et hat. this is the dot product on the right side of equation. Same thing, dot product on the left side of equation. Et hat. Okay, now we have this dot product on both sides of equation. We can keep simplify this. We can put this dot product into this parenthesis. Let's see what we end up with. Yeah, end up with v dot e dot plus v squared over rho en hat et hat. Okay, on the other side, just copy f times et hat. Alright, if you look at this, et dot et, that's the same unit vector. The dot product of the same unit vector give you 1. That's 1. And et and en dot product. This two dot product has a perpendicular direction to each other. Remember, en or et, between them the angle is 90 degrees, so the product is 0. Therefore, we end with m dot v dot times 1 plus 0. On the other side, copy f times et hat. Okay, let's move on. We're good. I think we're good here. Alright, and let's keep looking at this v hat. What is v hat? What's a variable with a hat, with a dot, sorry, v dot, excuse me. V dot means take this v with respect to time, right? Derivative of v with respect to time. Let's write it out. It equals m times dv over dt. dv over dt. Okay, what is dv over dt? That's v dot. And we can use chain rule to add a term that is ds here to create this m times dv over ds times ds over dt. So they're equivalent, right? The ss can cancel off, then you end up with dv over dt. So this whole thing is equivalent to this dv dt. We had a trick like this previously. And if you look at this ds dt, what is that? That is derivative of distance with respect to time. That will give you velocity, or that will give you speed. So we can change that, replace that with speed. So then we end up with f et hat equals m v dv ds. Okay, so this is something we end up with. Right, let me bridge this and land up both. Okay. Now let's put this ds on the other side equation. So times ds on both sides of equation, and you will end up with sum of the forces. Forgot this. Et hat equals, oops, excuse me, times ds equals mv dv. Alright, if we can take derivative on both sides of equation like this, then on the left side of equation, the derivative of the integration is with respect to ds, which is the distance. on the right side of equation, the derivative is respected to the speed, and in that way we could further simplify this. We can simplify the right hand of the equation to mv2 squared over 2 parentheses minus v1 squared over 2. That tells you the change of kinetic energy. Other set of equation, that is sum of forces et direction times with respect to ds. Okay, so now we end up with this. Okay, we're very close to our work energy equation. We can define this whole thing on the left side of equation as u1 to 2, and that means the work done from position 1 to 2. Position 1 to 2. And this whole terms here, it's a change of kinetic energy. Oops. Oops, sorry. Okay, never mind. Let's work. Okay. This can be represented as T2 minus T1, and that is change of kinetic energy. Kinetic, E-N-E-R-G-Y. All right, and boom, let's add an equal sign in between. Here, right here, this is our work energy equation. Work energy equation. Okay, we're going to use this equation to solve a lot of problems. And something to be noted is this work energy equation. It's a scalar equation that looks at how forces related to speed over a given position change. So once again, this is a scalar equation. Let's write it down. Scalar equation. Sorry about my writing. And it looks at how forces relate to speeds over a given position change. Okay, so F equals AM integrated once with respect to position. Okay. Some of you may have the question is, how come this is a scalar equation? Yeah, if you look at inside of this, the left side of equation here, v2 squared over 2, v1 squared over 2, and yeah, there's the velocity here, they're all speed, those are scalars, those are not vector. So what is happening there? So how come we end up with a scalar equation? So let me show you how. And do you remember what we did is we start with a scalar equation right here. Oops. We start with this scalar equation, vector equation with vector on both sides of the equation. Then what we did is we dot product et hat on both sides of the equation. So once you dot product this um, unit vector, you kind of like what you did to the whole equation is you transferred this equation into a scalar equation, because the dot product get rid of the unit vector instead of this acceleration. Yep. Okay. So let's remember the work energy equation is a scalar equation. It's a little bit different from what we did previously. We used a tons of vector equations before. Okay. So this is the introduction of the work energy equation part 1.